Okay, in this video we're going to look at section 5-2, growth and decay models. The assignment for this section in the book on page 382, 3 problems, and then there are 3 on WebAssign. All right, growth and decay, 2 bullet points here. Use separation of variables to solve simple differential equation. And actually 5.3, the title is separation of variables, so it's kind of weird. We're going to be doing that before the section that officially introduces it. And we'll use exponential functions to model growth and decay in real life applied problems. All right, back in 5.1, we learned to analyze the solutions visually of differential equations using slope fields. We did not do the Euler's method. Analytically, we've learned to solve only 2 types of differential equations. Those in the form of y prime equals some function, and where the second derivative, y double prime, is equal to some function. In this section, you will learn how to solve a more general type of differential equation. The strategy is to rewrite the equation so that each variable occurs only on one side of the equation. We'll get all the y's and dy's on one side, all the x's and dx's on the other. This strategy is called separation of variables, which we'll study in more detail in the next section. So let's see here. Example 1, solve this differential equation. We've got y prime equals 2x divided by y. Now, throughout the school year, I have been singing the praises of Leibniz, especially the Leibniz notation. Here's where it comes in very handy again. I'm going to take out this y prime and replace it with the superior dy dx. The derivative of y with respect to x is equal to 2x over y. Now, we just saw in that last slide there talking about separation of variables. So again, we want to get the x's and the dx's on one side, the y's and dy's on the other. And in this particular problem, it's nice and easy to do if we just remember how to cross multiply. So if I look here on this diagonal, the y's and the dy's are on the same diagonal, so I can just multiply y times dy is equal to, multiply on the other diagonal, 2x times dx. 2x dx. So in this case, it was real simple. We have our variables separated. Now, if we do something to one side of the equation, like antiderive, we got to do the same thing to the other side. And on the left here, if I antiderive y to the first with respect to y, I'm going to get y squared over 2. And remember, there would be a plus c. We'll call it c sub 1. And on the other side of equals, we'll antiderive here with respect to x. So we'll raise the exponent by 1, divide by the new exponent. 2x squared over 2 is just going to be an x squared. And we're also going to add a constant over here, plus c sub 2. Now, usually as these problems develop, we're just going to combine both of these constants on one side. Usually you'll see the calc books do it, when we antiderive the y, we'll leave it alone over here. And when we antiderive the other side with the x's on it, that's where we'll just add one constant. But realize, if we went through every step, we'd add a c to both sides, combine both of those constants into one other constant. And usually also you'll see the books will want to clear out any fractions. So here on this left side, we got a y squared over 2. If we multiply through by 2, we'll just get this down to y squared equals. If we multiply the other side by 2, to be fair, we're going to get a 2x squared there, plus 2 times some unknown constant is still just some other unknown constant. So there's our final answer to that one. So now here's how the book did it. Immediately in our first step, we changed that y prime into dy dx, the Leibniz notation. Here's how the book does this example. There they multiply both sides by y, and then here they kind of make this that dy is y prime dx. So notationally what they go through here in the book is a little different, and I think it's a little more confusing. I just jump right to the Leibniz notation. And now that leads us into the big part of this section, the growth and decay models. And it says in many applications, the rate of change of a variable y is proportional to the value of y itself. So let me highlight this. It's a key phrase to watch out for, especially on the AP test. The phrasing on here tells us a lot. Let me just read it again. The rate of change of y is proportional to the value of y. When y is a function of time t, this proportion can be written as shown. So here we're going to translate the rate of change of y, dy dt, is equals proportional to y. So we're going to take y and multiply it by some constant k, and that k we'll see is called the constant of proportionality. So the general solution to this general differential equation is given here in the next theorem. Theorem 5.1, and it says if y is a differentiable function of t such that y is positive and y prime is equal to k times y for some constant k, that's its constant of proportionality, then y is equal to c times e to the kt power, where c is the initial value of our y and k is the proportionality constant. Exponential growth occurs when that k is greater than 0, when it's positive. Exponential decay occurs when k is less than 0, or a negative number. Now think back, if we were graphing in pre-calc, we had our exponentials. We could use base e or any number. If it was 2 to the positive x, we had exponential growth where we went up. And if we had a negative exponent, 2 to the negative x, that's where we went downhill, exponential decay. But if you look at this theorem here, you don't see any calc in it on its surface. We just see y equals c e to the kt. We dealt with e in pre-calc. C is just a number, k is just a number, and t is our time value. So on the surface, it looks like there's no calculus here. But in fact, the calculus is baked into this equation. And we haven't done many proofs in calculus. You won't see any of them on the AP test. But here we're going to do this proof to show how the calculus is baked into that equation we just saw in the theorem there. So here's we're going to start with the rate of change of this. The rate of change of y is proportional to y itself, k times y. First, let's get rid of the prime notation. That'll become dy dt. And let me switch. I don't like it. Go back to black ink. So y prime, or dy dt, is equal to some number k, some constant k, times y. Okay, first thing I'm going to do, multiply both sides by dt. So now the dt is on this side. And to get my y's together, I'm going to divide both sides by y. So now I have dy over y is equal to k times dt. And at this point, I am going to antiderive each side. And keep in mind k is just a constant. On the left side, this form should look familiar. Dy over y, or y prime over y, or u prime over u. The left side will antiderive to the natural log of y. And we could put a plus c on there, but again, we're going to save that here for the other side. When we antiderive here, k with respect to t, that's going to become kt plus our constant c. Now what we want to do here is solve for y. So we're going to exponentiate each side, raise it to a base e. E to this exponent, and it's positive. We can drop the bars at this point. So over here, we're going to have y equals e to the kt plus c. E to the e to the kt plus c. Now pay special attention to this next part. You'll see this pop up. You'll need it as you're solving some of these problems. Over here we've got e to a two-term exponent, e to the kt plus c. That's all in the exponent. When do we add exponents? When we multiply like bases, like x squared times x to the third would be x to the fifth. When we multiply the bases, we add the exponents. So we could rewrite this as e to the kt power times e to the c power. E is just 2.72. That's one of our irrational numbers. E to the c power, remember c is just some unknown constant. So this e raised to the c power is just going to turn into another constant. And we're going to move that constant here in front. So we can rewrite this as y equals c times e to the kt power. And that's our theorem from the theorem box. So here, this y equals ce to the kt, that has the calculus baked in. And remember, for this to apply, we have to have the rate of change of something is proportional to it to begin with. So if that is the case, we can use this theorem, y equals ce to the kt, and the calculus is baked in. So since we have this new theorem, let's take it for a test drive. It says here at the start of the example, the rate of change of y is proportional to y. So as soon as they make that statement, that says it's legal for us to use this theorem 5.1, y equals ce to the kt. And then it goes on to say when t is 0, y is 2. When t is 2, y is 4. So they gave us two initial conditions, 0, 2 and 2, 4. And they're asking us what is the value of y when t is 3. So using the first two conditions, we're going to create a model. And then using the model, we will predict what y is when t is 3. So graphically, what's going on here, we've got 2 points, 2 comma 4 and 0 comma 2, and they've told us that the rate of change of y is proportional to y. So we can use those 2 points to establish the curvature of this specific exponential growth model. Once we have that model, we can use it to figure out this point, 3 comma question mark. We can figure out the y value when t is 3. So again, they've cleared the way for us to use our equation, y equals ce to the kt. So a way I like to introduce these problems is I'm going to write it out twice, y equals ce to the kt. I don't like that k. Oops, get back there. Kt. And I'm going to write it again over here. Now we've got two initial conditions, and the beautiful one is right here, times 0. 0 comma 2. So we're going to use this point over here, y is 2, when t is 0, so that'll become a k times 0. We'll use this one to solve for c. And 0 times k is 0, so this becomes e to the 0, and anything to the 0 power is 1, so this just says c times 1 is 2, or c is 2. Now since we've figured out c is 2, I can replace this c with a 2, and we've got another point, let me switch to blue ink, 2 comma 4. So I'm going to replace this y with a 4, and the t with a 2. So this becomes 2k. Now let's solve for k. Divide by 2. 4 divided by 2 is 2. 2 equals e to the 2k. All right, we want to solve and get k by itself. How do we get rid of the base e? Natural log. So I'm going to move up here. The natural log of 2 is equal to ln and e cancel, so the answer over here is 2k. 2k. To get k alone, divide by 2. K equals natural log of 2 divided by 2. Now let's find this as a decimal here. K is approximately, and we always take things to at least 4 spots in calculus. Here when we punch that on the calculator, we get approximately 0.3466. So we first found our c value. That was easy. That was 2. And now we've found our k value. So our blank formula, y equals ce to the kt power, is now y equals 2e to the point. This thing doesn't do decimals very well. There it is. Y equals 2e to the point 3466t power. So with this, we now have our model. Again, let me get this out of the way. Graphically, what we've done, we used the two given points to establish the curvature of this line. Now that we have our model, we can use it to predict what's going on out here when t is 3. So the second part of this, they want what's the value of y when t is 3. So y equals 2e to the point 3466 times 3. And we punch this in our calculator, and we get y is approximately 5.657. And if I use my graph just to sort of gauge the reasonableness of the answer, if I go over from that y, yeah, it's definitely a number less than 6, a little closer to 6 than 5, and my answer makes sense. So we use the formula twice with the two conditions. First, the time 0 to get the c value, and then using that c value in the other point, we solve for k. Now here we have radioactive decay. We measure that in terms of half-life, or the number of years required for half of the atoms in the sample to decay away. The rate of decay is proportional to the amount present. The rate of decay is proportional to the amount present. So that tells us we can use our new formula, y equals ce to the kt. Now here below we have some half-lives of common radioactive isotopes. Uranium, almost 4.5 billion years. Plutonium, 24,100. Carbon, 5,715 years. If you've ever heard carbon dating, they can figure out how old some stuff is by the decay of carbon. Radium, about 1,600 years. Einsteinium, less than a year. Radon, 3.82 days, and nobelium decays, half of it disappears every 25 seconds. All right, and that gets us into here, example 3. We have 10 grams of the plutonium isotope that was released after a nuclear accident. How long will it take for those 10 grams to decay down to 1 gram? Okay, now they did give us, let's see here. Let's let y equal our mass of plutonium. Y equals the mass of plutonium in grams. And they even, we know from the previous slide there about the radioactive decay, that the amount, or the decay, is proportional to the amount. So we can use our formula, y equals ce to the kt. Now they did give us some points. At time 0, when our problem begins, we have 10 grams. So remember, our y value is our mass of plutonium. At time 0, we have 10 grams. So we can solve for c. Y is 10 equals ce to the k times 0. Anything times 0 is 0. E to the 0 is 1. And then 1 times c is c. So we get c is equal to 10. And we can update our equation. Instead of y equals ce to the kt, y equals 10e to the kt. So now this brings us to the question, where's our next point? We need another point to jump in here and solve for k. Plutonium. Plutonium is right here. It takes 24,100 years for half of it to decay away. So remember, our points here are t for time, y for the amount of plutonium. We had at time 0, 10 grams. So if we let 24,100 years pass, we're going to be down to half the amount we had before, from 10 grams to 5 grams. So now we've got our next point to plug in here and solve for K. So our Y value is now 5 is equal to 10 E to the 24,100 times K. I don't like my pads getting glitchy. There we go. All right, we want to solve this for K. Step 1, divide by 10. 5 divided by 10 is a half. 1/2 equals E to the 24,100 K. And to get rid of the base E, we're going to natural log each side. The natural log of a half is equal to 24,100 K. And to get K alone, we're going to divide by 24,100. Now, if we punch that in, because that's pretty confusing just to throw up in there in our exponential equation. So let's find this as a decimal. Now, I always say round to 4 spots. If you round this to 4 spots, you're going to round it to 0. Always go 4 decimals after the zeros end. So here our K value is approximately negative 4 zeros, 0, 0, 0, 0. And now that the zeros are done, we want at least 4 spots, decimal places and numbers. 2876. 2876. So that's our K value. So our blank equation, y equals CE to the KT, is now y equals 10 from our first initial condition, E to the exponent negative 0.0002876 t. So we use the given information to come up with our model. Now we can use the model to answer the question, how long will it take for the 10 grams to decay to 1 gram? So they're asking us in sort of the form of a point. Our Y value, remember, is how many grams of this isotope we have left. We started with 10. Now we want to get down to 1. So we want to find the time it takes to get down to 1 gram. So we're going to be solving for this T after we make our amount of plutonium to 1. So 1 equals 10 e to the negative 0.0002876 t. Step 1, divide by 10. So this is now 1/10. And over here is a base E, so we're going to natural log. Natural log of 1/10 is equal to negative 0.0002876 t. And now I can sort of do this on my mimeopad here. We're going to divide, both sides by this amount, this negative very small decimal. So t is equal to the natural log of 1/10 divided by that very small negative number. Beep, beep, beep goes the calculator. T is approximately 80,059.28 years. So at time 0, we have 10 grams of plutonium. Every 24,100 years, half of it decays away. To get from 10 grams down to 1 gram, it's going to take just a little over 80,000 years. Now, what's this down in the corner? From example 3, notice that in an exponential growth or decay problem, it's easy to solve for c when you're given a time value at t0. This next example demonstrates the procedure to solve for c and k when you don't have your time 0 initial condition. So here we're going to kick it up a notch. It's not computationally much harder in my opinion. It's just a little different process. So here it says we have an experimental population of fruit flies. It increases according to the laws of exponential growth. There's 100 flies on the second day, 300 flies on the fourth day. Use that information to back up and figure out approximately how many flies were in the original population. So again, we have two initial points. Usually one of them is the time 0 point, which makes it nice to establish the curvature. But now we have two non-time 0 points. We can still use those points to establish our curvature and work backwards to find our time 0. And if we're nice enough to have the graph, we can see our answer is somewhere between 25 and 50, a little closer to 25. So here we go. So let's flesh out our points here again. 100 flies on day 2. So we've got a point 2 comma 100. And then we've also 300 flies on the fourth day, time 4 flies 300. So, I've spread it out here, the 2 points, and we are going to use the same formula twice. Y equals CE to the KT. So let's use this first point and see what we can get done here. Our y value is 100, and our t value is 2k. Let's solve for c. Divide by e to the 2k. E to the 2k. So I'm going to have this c by itself now, so c equals, and I'm going to rewrite this so it's not in the form of a fraction. The 100 is in the numerator, it's going to be fine. I'm going to bring up the e to the 2k. What happens when we bring it up? The exponent switches sign, now it's negative. So over here, using the same formula, y equals c e to the kt, I've got this y value, 300 is going to go in, equals. Now for c here, I can replace c with this, 100e to the negative 2k. And then I still have this piece, e to the kt, e, and we're plugging in t as 4. So this will be 4k. Okay, now if we look at this here, the only thing left that we don't know is our k value. So we can solve this for k. Once we've got k, we can back up and solve for c. So let's simplify this. 300 equals, see, we've got 100 times 1, so we'll still have 100. We've got a base e times a base e, so the answer will be a base e. Multiplying the bases, we add the exponents. Negative 2k plus 4k is 2k. Now let's solve for that. Divide by 100, so now it's equal to 3. And to get rid of the base e, we're going to natural log. The natural log of 3 is equal to 2k. And to get k by itself, divide by 2. Natural log of 3 divided by 2. And let's turn that into a decimal. Natural log of 3 divided by 2 is approximately 0.5493. So we've got our k value, and now we can go back and solve for c. And we can use either of the given points. We have y equals c e to the kt. I'm going to use the smaller point, 2 comma 100, just because the numbers are smaller. So we've got 2 comma 100 for our t value and our y value, and now we have k right here. So y, or 100, is equal to c e to the 2 times 0.5493. 3. And to get c by itself, we're just going to divide by e to 2 times this, or it's going to wind up on the other side as a negative exponent. 100 times e to the negative 2 times 0.5493 is equal to c. And you just punch that in your calculator, and you get approximately 33. Remember, we're talking fruit flies, I can't remember what the exact decimal is, but since we're talking about bugs, we round it to the nearest whole bug. Approximately 33 fruit flies. Now, example 5, another good example here, and they do start us with a time 0 initial condition, but this is going to model decay. So it says here, 4 months after it stops advertising, a manufacturing company noticed its sales have dropped from 100,000 units per month to 80,000 per month. The sales follow an exponential pattern of decline. What will the sales be after another 2 months? So they do say that the rate of change is proportional or an exponential pattern of decline. Well, we're not going to use the y equals ce to the kt on this one. That is correct. That's right. 4 months after sales decline drop 100,000. So the rate of, oh, I'm looking at the wrong page in my notes. Oh yeah, we are going to use. I'm an example ahead. This does follow exponential decline, so it will be y equals ce to the kt. And let's figure out our points here. So at time 0, when this problem begins, we're selling 100,000 units per month. And then 4 months after we stopped advertising, so time is now 4, we've gone down to 80,000 units per month. So we are following an exponential pattern of decline. What will the sales be after another 2 months? So now we got to be careful with the wording here. We went from 0 to 4 months after another 2 months. It's going to be 6 months, and we want to know what our sales are expected to be. So we'll use the first 2 points to establish the curvature of our exponential. And then after we have that, our model, we'll use it to make our prediction about what's going on in the 6th month. So let's use our original time 0 condition to solve for c. I bet you already know what it is. Oops. Y 100,000 is equal to c times e to the 0 k. 0 times k is 0. E to the 0 is 1. C times 1 is c. So our c value is 100,000. Now we're going to use c as 100,000 and this point to solve for k. So y 80,000 equals c 100,000 e to the 4k. So to solve for k, divide by 100,000. So 80,000 divided by 100,000 is 0.8. We'll just use a decimal on this. 0.8 or 8/10 is equal to e to the 4k. Take the natural log. The natural log, I'm going to do it as a fraction because I'm having trouble drawing decimals with my pad here. The natural log of 0.8 or 4/5 is equal to 4k and divide by 4. So k is equal to the natural log of 0.8 divided by 4. And if we turn that into a decimal, k is approximately 0.05 negative. Oops, yeah, we got to have a negative in there. Negative 0.0558. So our model, y equals 100,000 e to the negative 0.0558t. Now again, we want to use our model to predict what's going to happen in 2 more months, or again, that's what time is 6. So we put a 6 in for T, and you punch that in on your calculator. Y is approximately 71,500 units. And that makes sense because our sales are declining. We've stopped advertising. Here after 4 months, 80,000. As some 2 more months go by, we're definitely going to be selling less if we're not advertising. Okay, now for the grand finale. I think this is the last example, yeah. So it says here in those examples 2 through 5, you did not actually have to solve a differential equation in this form. Y prime equals k times y, or the change in y is proportional to y itself. Because we did it in the proof of the theorem. We baked the calculus in. The next example here demonstrates a problem whose solution involves the separation of variables technique, and this example concerns Newton's law of cooling, which states that the rate of change in the temperature of an object is proportional to the difference between the object's temperature and the temperature of the surrounding medium. So think about this, if the room temperature is 80 degrees and you pull something out of the oven that's 200 degrees, that gap is very big. So very quickly it starts to cool fast. But as it gets closer and closer to room temperature, that change will slow down. Eventually it will achieve room temperature, but because it's so hot to begin with, it starts cooling very rapidly. And then as it approaches room temperature, it slows down. So it says here in example 6, let y represent the temperature degrees Fahrenheit of an object in a room whose temperature is kept at a constant 60 degrees. The object cools from 100 degrees to 90 degrees in 10 minutes. How much longer will it take to decrease down to 80 degrees? So again here we have y prime. Or no, let's not do it like that. We know that the rate of change is proportional to the difference between y, the temperature of the object, and 60 degrees. So rate of change is proportional to the difference to the diff between y and 60 degrees. Y is the temperature, the thing that we're taking out. 60 degrees is our room temperature. So the rate of change, y prime, is equals proportional to the rate of change is proportional to the difference between our temperature and 60 degrees, y minus 60. So the rate of change is proportional to the difference between the temperature of our object and the 60-degree room temperature. So there, coming up with the equation based on the verbal model might have been the trickiest part. And let's move this up here. And of course, we're going to take out the y prime, replace that with dy dt. And since dt is on the bottom, we'll multiply both sides by that dt. So now it's on the other side. And to get this as a quantity on the other side, we're going to divide both sides by that quantity. So dy divided by quantity, y minus 60, is equal to k dt. And at this point, we are ready to anti-derive each side. On the left, it's u prime over u, or y prime over y. So this left side can just anti-derive to the ln of our denominator. We can drop the absolute value bars because our temperature here is above 60. It's never going to cool below room temperature. So this value here is always going to be positive. And when we anti-derive over here with respect to t, that will become a k times t plus our constant. Okay, time to exponentiate each side. So if we base e here, we're going to get y minus 60. And over here, we're going to base e. Remember, this turns into one big exponent. So this is going to be e to the kt power. And instead of the plus c, we can make it times e to the c power. And this e to the c just becomes another constant. So this becomes c e to the kt. See, now this is sort of like the proof from before, but we got this y minus 60 on the other side. At this point, I guess we can use our initial condition. At time 0, I believe it was 100 degrees. Yeah, we pull it out. It's 100 degrees. So 0, comma 100 is our initial point. So we're going to use the point 0, 100. Y becomes 100. 100 minus 60 equals c e to the 0k. 0 times anything is 0. E to the 0 is 1. So c is 100 minus 60 is 40. So we've got c is equal to 40. I can rewrite my equation then as y equals, well, if I back up here, I'm just going to add that 60 to both sides. So I got y minus 60. I'm going to add the 60 to both sides and then plug my other values in. So that's going to look like this. Y equals 60 plus, and instead of ce to the kt, it's 40 e to the kt. So now I can use my second point. 10 minutes have gone by and it's down to 90 degrees. So time is 10, temperature is 90. So 90 goes in for y. 60 plus 40 e to the 10k. And we want to solve for this k. So let's see here, subtract 60. So now this is down to 30. We're going to divide by 40. 30 divided by 40 is 0.75. Or I'll just write it as 3/4. 3/4 equals e to the 10k. Take the natural log. The natural log of 3/4. Natural log here cancels the e. 10k. And I'm just going to work back up here, get my k on the left. So the natural log of 3/4, all divided by 10. And as a decimal, k is approximately negative point, come on, decimal, 0.02877. So we found our k value, we found our c value. We can create our model. Y equals 60 plus 40. We found our c value is 40. E to the negative point 0.02877 t. So let's look at our problem again. How much longer will it take to decrease to 80 degrees? So remember, y is our temperature. We want to know, as it hits 80 degrees, what was the time involved? So we're going to change that y to an 80 and then solve this for t. Okay, let me move this up. So let's see here, we're going to subtract 60, 80 minus 60, this will be a 20, and then we're going to divide by 40. 20 over 40 is 2/4 or 1/2. 1/2 equals e to the negative point 0.02877 t. Take the natural log. Natural log of a half is equal to negative 0.02877 t. Divide by this decimal, negative 0.02877, and we get our t. t is approximately 24.09. Now on the AP test, this would probably be decoy answer A in the multiple choice, because let's go back and reread the work here. So it went from 100 to 90 in 10 minutes. How much longer will it take to decrease to 80? So this 24 minutes includes the 10 minutes it already took to go from 100 down to 90. So to figure out how much longer will it take, we'll subtract out that 10 minutes and see that it's going to be about 14 more minutes, approximately 14 more minutes to cool down to the 80 degrees. And here's what we were looking at graphically. So we take the object out, it's 100 degrees. It takes 10 minutes to get down to 90, so that established our curvature. And then we figured out, okay, how much longer to get down to 80 degrees. So we extended that out using our model and found out it was going to be 24 minutes to get to 80 degrees, or about 14 more minutes. And that's the end of this video. I'll probably put another one together to go over some odd problems here.